Okay, let's start. Assume A is the smallest. And also, A does not equal 1. So, i.e., all right, yeah, that 1 is not the smallest. It's not A. i.e., the smallest is less than 1. Okay, now, if you multiply by A, you get A squared is less than A. And so, A squared is the smallest, which contradicts unless the smallest is 1. So we have, i.e., we have to allow the smallest to be 1. Because, for example, no, I think we'll just leave it at that. Yeah, yeah. Yeah, because let's run through this again, but we say also 1 is the smallest. So that means A equals 1. And then when you multiply both sides by A by 1, this is true because 1 multiplied by itself is 1. So maybe it's not the best proof, but it'll do, I think, I hope. I don't know how rigorous we have to be here. Okay, so let's start off with the second part then. So use this principle should apply to principle, i.e., so S is a subset of N. One is in S, and if N is in S, so is N plus 1 in S. Okay. So we know that, okay, so let's begin. 1 is in S. So that implies 1 plus 1 is in S. But 1 is the smallest. And so 1 plus 1 can't equal 1, and 1 plus 1 is greater than 1, i.e. 2. So that then would mean if 2 is in it, then 2 plus 1 is in it. But again, this is not the smallest. So 3 is more than 1, and 3 is more than 2, since I think we can take it for a fact and axiom. N plus 1 is greater than N. Continuing, would lead to S equals N. I wonder, yeah, I mean, if you could maybe show by contradiction, every element is in it. For example, maybe assume M plus 1 is not in S, and that would show that S does not equal N. Well, then that would imply M is not in S, which would imply M minus 1 is not in S. And we'd continue to the least. So you'd get 1 is not in S, but that then would contradict the start. So I don't know. I guess it's all right. I don't like these proofs. I really don't like these proofs because we're stepping into the... okay. I just don't like them.